Hello, everyone. This section of notes is going to cover chapter 7.6 to 7.8. In previous sections, we introduced substitution and elimination reactions and then focused on SN2 type reactions. Here, we're going to be focusing on E2 reactions, which are one of the two elimination reactions we're going to study. So, alkyl halides being our substrate can be treated with a strong base to undergo elimination reactions in addition to substitution reactions. We call this a beta elimination or 1,2 elimination to form alkenes. So you have your alkyl halide, which can be treated with a base that undergoes the elimination to form the alkene. The strong base will react in a concerted mechanism to give the E2 elimination. Now, if you recall the mechanism patterns that we learned in chapter 6 and we've been using since, the two that we're going to focus here are proton transfer and loss of a leaving group. So the proton transfer occurs when the base takes that proton and the electrons are used to create that carbon-carbon pi bond, and then we have the loss of the leaving group. And that gives us our beta elimination. So your alpha carbon has the halide and your beta carbon has the proton that's being extracted. The beta 1,2 elimination, like I said, is simply a proton being removed from that beta position. The leaving group leaves with a pair of electrons and your double bond is formed. So the beta elimination is just your simple E2 elimination, and then we also have some more specific characterizations of elimination reactions. We have a dehydrohalogenation, in which the leaving group is a halogen, and then we have a dehydration, in which the leaving group is a water molecule. Both good leaving groups, and both can undergo these beta 1,2 eliminations. So let's look at the rate law of an E2 elimination. The E stands for elimination, and 2 means bimolecular or second order. And if you recall, the sum of the individual reactant orders is equal to the overall reaction order. So 1 plus 1 equals 2. We can see that the rate of an E2 reaction depends on the concentration of the substrate, alkyl halide, as well as the concentration of the base. So the nature or characteristics of our substrate, the alkyl halide, can affect how quickly the elimination proceeds. So let's look at a tertiary substrate, which is unreactive in an SN2 reaction, but very reactive for an E2 reaction. So in our substitution reaction, the hydroxide cannot access the electrophilic carbon, right? It's too sterically hindered, so that does not occur. However, with an elimination, the hydroxide doesn't have to attack the carbon, it just needs to get to the exterior proton, so the removal of that proton is much easier with a tertiary substrate. So hydroxide can't act as a nucleophile with a tertiary substrate. However, it can function as a base because it doesn't have to deal with the steric hindrance or the bulkiness around that electrophilic carbon. Tertiary substrates are the most reactive for E2 eliminations. Primary substrates are least reactive. And we can understand this by looking at the energy diagram. So if you see the activation energy is lowest for a tertiary substrate, with the activation energy being the highest for a primary. In order to further understand these elimination reactions, we have to take a pit stop and understand the stability of alkenes. So let's first look at cis versus trans. Cis versus trans isomers. Cis isomers are less stable than trans isomers, which are more stable. And this has to do with steric hindrance and steric strain. So there's more strain put on these bond angles because of the bulky methyl groups being on the same side. But when you have your methyl groups on opposite sides, there's less steric strain, making it a lower energy, more stable alkene. We can also look at this quantitatively through heats of combustion. Remember, a lower heat of combustion means greater stability and lower potential energy. So the trans versus the cis, the trans has a lower heat of combustion. The cis has a higher heat of combustion. That means that there was less potential energy stored in the bonds of the trans molecule, meaning it's lower energy, more stable. In addition to the steric effects of cis and trans, we also have to take into consideration the degree of substitution when comparing the stability of alkenes. So we're going to look at the alkyl groups attached to the carbon-carbon bond. So alkyl groups stabilize the carbon-carbon pi bond through hyperconjugation. Remember, that's donating electron density. So when we look at substitution patterns, you can think of any alkene having four things attached. 1, 2, 3, and 4. And to get the substitution pattern, we're simply going to count the non-hydrogen groups. So we have 4 positions. And we're going to count the non-hydrogen groups. So let's look at the first alkene. There are 2 hydrogens here. Or sorry, 3 hydrogens on that alkene. And then 1 non-hydrogen group. So because there is 1 non-hydrogen group, we say it's monosubstituted. Let's look at the next one that's disubstituted. Let's put the hydrogens in. There's 2 hydrogens and 2 non-hydrogen groups. So it's disubstituted. Let's move on to a more stable alkene. We're going to put our hydrogen in. So there's 1 hydrogen and 3 non-hydrogen groups or alkyl groups or substituents. Anything aside from a hydrogen, okay, we count. So because there are 3 non-hydrogen groups, it's trisubstituted. Let's look at our final alkene. There are no hydrogens, and we have 4 methyl groups, or 4 alkyl groups, 4 non-hydrogen substituents around the carbon-carbon double bond. So because there are 4, that's tetra. The greater the substitution pattern, the more stable the alkene. The lower the substitution pattern, the less stable the alkene. So as we increase our substitution, we increase the stability of the alkene. And remember, you're simply looking at the number of non-hydrogen groups around that carbon-carbon bond. So you can think of that as a template. Let's look at this example here. We're going to arrange the following isomeric alkenes in order of stability. Isomeric meaning they have the same chemical formula. Well, on our first one, we have, let's look at our alkene, carbon-carbon. We have 2 hydrogens. And then there are 2 non-hydrogen groups about the carbon-carbon double bond. That's why this one's di-substituted. In our next alkene, carbon-carbon double bond, we have 1 hydrogen. There are 1, 2, 3 non-hydrogen groups. It's tri-substituted. And let's look at our final alkene. We have our carbon-carbon double bond, 1, 2, 3 hydrogens, and this whole thing is 1 substituent or 1 non-hydrogen group around the carbon-carbon double bond. That's why it's mono-substituted. Now, if we want to rank these in order of stability, we learned that as we increase the substitution pattern, we increase stability. So, a tri-substituted will be the most stable, and a mono-substituted will be the least stable, where di-substituted is in the middle. Okay, now that we've introduced the E2 mechanism and the effect of the substrate, the kinetics, and alkene stability, let's take a look at the regio and stereochemical outcomes for E2 reactions. So we're going to be looking at regioselectivity, stereoselectivity, and stereospecificity. We're going to look at 3 things. And we have to understand these and be able to predict the regio-stereoselectivity and stereospecificity for a given E2 reaction. Let's start with number 1, regioselectivity. Regioselectivity occurs when one constitutional product is formed predominantly over the other. That means when you can get 2 products or more than 1 product, one will be your major and one will be your minor. So we typically get a major product and a minor product because more than 1 product can be formed. We know that regioselectivity will be an issue and that we will get more than 1 product when multiple reactive sites are present. If multiple reactive sites are present, we get multiple products. So what constitutes as a reactive site? A beta proton. All right, so when you have more than 1 beta proton that can be removed. Okay, so different beta sites can be deprotonated to give different alkenes. For example, let's look at our beta protons on the molecule below. On the left, we have a carbon that has 1, 2, 3. We say that we can consider these to be equivalent beta protons. All right, so we've got those, and then we've got 2 over here. Now my base can remove one of these, and I get my alkene here. Or let's draw these back in. Or the base can remove one of these protons and afford the alkene above. We have multiple reactive sites in the molecule because I have different beta protons that can be deprotonated. So, when we get two different products, we need to be able to characterize them. We're going to characterize them as a Zaitsev or a Hofmann product. The Zaitsev product is the more substituted alkene. Let's look at the substitution pattern. On my carbon-carbon double bond, there's one hydrogen and 1, 2, 3 non-hydrogen groups around it. So this is a tri-substituted alkene. And let's look at the alkene below. I have a carbon-carbon double bond. We have 1, 2 hydrogens and 1, 2 non-hydrogen groups. So this is a di-substituted alkene. The Zaitsev product is whatever product is more substituted. The Hofmann product is the one that is less substituted. So tri-substituted is greater than di-substituted. So that's why we call this tri-substituted the Zaitsev product. So different beta protons can be deprotonated to give different products. The one that is more substituted, we call the Zaitsev product. The one that is less substituted, we call the Hofmann product. Now we're going to learn how to predict which will be the major and minor product. The product distribution depends on the steric hindrance or type of base that we're using. So, bulky bases versus non-bulky bases. All right, so ethanol or ethoxide, this is a non-bulky base. And we primarily get the Zaitsev product. But a bulky base or sterically hindered base, in both cases we get the Hofmann product. So to summarize, bulky bases afford the Hofmann product and non-bulky bases give the Zaitsev product. All right, so we're going to make this easy. Non-bulky bases are going to be any alkoxides, any small or short chain alkoxides, like MEO minus or ethoxide, methoxide, ethoxide. You might also see them written like this, NaOMe or NaOEt. Remember sodium, these group 1s are just spectators. You might also see a non-bulky base like a hydride or hydroxide. Non-bulky bases are small bases. They have small carbon chains or no carbon chain at all. The bulky bases are going to have large substituents attached to the basic molecule or basic atom. So bulky bases have a harder time getting into, let's draw our beta protons, have a harder time getting into the more sterically hindered beta sites. So a bulky base has a hard time getting to these protons here because we have a methyl group around it, all right? But a bulky base can more easily access these exterior beta protons, which are not hindered. So your bulky base will go after the protons that are more easily accessible. The non-bulky base can get into the more crowded beta site. More crowded or more sterically hindered beta site. So we know what product is going to be formed depending on the type of base that is used. So in summary here, a less hindered base will give the Zaitsev product. A more hindered base gives the Hofmann product. Non-bulky base, like sodium ethoxide, versus a bulky base, like potassium tert-butoxide. Do you see how the non-bulky base gives the Zaitsev product, which is the more substituted product? This is a tri-substituted versus a di-substituted. And a bulky base gives the Hofmann product as the major product, 72% compared to 28%, right? Di-substituted versus tri-substituted. Some other examples of sterically hindered or bulky bases. These are also called non-nucleophilic bases because they cannot act as nucleophiles. They're too sterically hindered. We already mentioned the potassium tert-butoxide, but some very common bases that we use in the organic lab are the amines, like diisopropylamine or triethylamine. All right, so let's look at a problem. If we want to identify the major and minor products, knowing that we're dealing with an E2 reaction, and we're given the base, right, which this is sodium methoxide. This is a non-bulky base. Let's draw our products. So this non-bulky base is already telling me that I'm going to get the Zaitsev product. I know that right off the bat. And it's going to be the more substituted alkene. So all I have to do is draw the products and then identify which one's more substituted, and that will be my Zaitsev product. So let's start with our molecule. All right, so the carbon that has the halogen is your alpha position. And let's look for multiple beta sites because regioselectivity will only occur when we have multiple beta sites. So there's a beta site, there's a beta site, which these two are actually identical, right? So let's not worry about this one. So here's a beta site, and then here's one too. Now let's look, we've got hydrogen, hydrogen, and then I've got a bunch of hydrogens here in the methyl. All right, so I can take either one of these. Let's start with this one. If my base, the sodium methoxide, I'll just write the methoxide out. If my base takes the proton, make sure you practice drawing this mechanism. This first set of arrows is going to put a double bond right here. And then you get the MEOH, your Cl minus All right, now what if my methoxide were to take that proton? Well, I would end up with this product. I've already established that sodium methoxide is a non-bulky base, and the major product will be the Zaitsev product. The major product will be the Zaitsev. So now let's look at the substitution patterns of the products that I've drawn. I've got an alkene that has 2 hydrogens and 2 non-hydrogen groups. This is di-substituted. And on the one below, I've got 1 hydrogen and 3 non-hydrogen groups. So the bottom product is my tri-substituted. Well, tri-substituted is a greater substitution pattern than di-substituted. And remember, Zaitsev is the more substituted, so this is my Zaitsev product. And the less substituted is going to be the Hofmann. And because I know that the major product is going to be the Zaitsev product, the bottom one here is major, and the Hofmann is minor. Right off the bat, I know what my major and minor will be by looking at the base. The base tells me, because it's a non-bulky base, it tells me that the Zaitsev product is going to be the major product. So all I have to do is draw both products and then determine which one is the Zaitsev and which one is the Hofmann, and I know which is major and minor. Let's do a couple more examples here. We're going to predict the major and minor products for the E2 reactions. So if you'd like to stop the video and try these on your own, you can do that, or you can just keep watching and I'll go through them. Step 1, let's look at the base and identify if it's a bulky or non-bulky base, and that will tell us right off the bat what product will be major. Sodium methoxide, this is a non-bulky base. So I know the Zaitsev product, or the more substituted product, will be my major product. All right, so let's take a look at our possible beta positions that can be deprotonated. Here's my alpha. I have a beta and a beta. Hydrogen, 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 hydrogen. So my ethoxide can deprotonate this beta site to give that product, plus my ethoxide could possibly deprotonate this other beta site to give this product. The first one is di-substituted. The second one is tri-substituted. So the di-substituted is my Zaitsev. The di-substituted is my Hofmann. And I know that I'm dealing with a non-bulky base, so the Zaitsev is going to be my major product. And the Hofmann will be my minor product. Let's look at the next example. Sodium hydroxide. This is also a non-bulky base. I know that the Zaitsev will be my major product. All right, so let's look at the different beta positions that I could deprotonate to get different products. The carbon with the alkyl halide is your alpha position. I have a beta here, and these two betas are the same on the methyls, so let's just worry about one of them. I've got two hydrogens, and then I've got three hydrogens on this methyl. My hydroxide could deprotonate one of these to give the following product. That's a di-substituted alkene. And let's look what happens if hydroxide deprotonates the other one. I get a tri-substituted. So because my hydroxide is a non-bulky base, it's telling me Zaitsev will be the major product. This tri-substituted is my Zaitsev product, which is my major product. The di-substituted is less substituted, that's the Hoffman. And that's going to be my minor product. Now, the example below is the same substrate with a different base. Potassium tert butoxide is a bulky base, so I know that the Hoffman product is going to be the major product. So I'm going to get the same exact products as I did above. But now my Hoffman, the di-substituted, becomes the major product because I've used a different base. And the Zaitsev becomes the minor product. So the nature of the base tells you what the major and minor products are going to be. So we just looked at regioselectivity, where we had different beta hydrogens on different positions or different carbons, and we had a product distribution. So regioselectivity, an easy way to think about this, regioselectivity, you can think of it when you have different beta hydrogens, okay, on different carbons. But when we have two beta hydrogens on the same carbon, we have a matter of stereoselectivity. So there are two stereoisomers that are produced in unequal amounts when we're dealing with stereoselectivity. So let's look. Here's our alpha position, and we have beta and beta. So each of the beta carbons have two hydrogens. Okay, so in this case, let's focus on only one of the beta positions because they're both identical. They both have CH2 groups. It's a symmetrical molecule. Now, stereoselectivity arises here because if I take this proton, I will get a different product than if I take this proton. So again, we know stereoselectivity will arise when there's two beta protons, okay, on the same carbon, and this will give rise to trans or cis products. So if you have two beta hydrogens on the same carbon, you're going to get a mixture of cis or trans. Trans will always be the major product, always. Trans is always the major. Cis is always the minor. The reason, because trans, again, is lower in energy. It's a more stable product than the cis due to the steric hindrance or steric strain. Stereospecificity is different. So we did regioselectivity when there were beta hydrogens on different carbons that we could remove that gave rise to our Zaitsev and Hofmann product. There was stereoselectivity where we had beta hydrogens on the same carbon that gave rise to cis or trans products, trans being the major, always. And then we have stereospecificity. And stereospecificity occurs when our substrate can only yield one stereoisomeric product. You can recognize stereospecificity in the situations where this arises when you've got a single beta proton that must be in a particular conformation that gives one very specific product. So, first thing to understand about stereospecificity, that the elimination reaction that occurs, the proton transfer and loss of a leaving group, must occur when our proton and the leaving group are in an anti-periplanar conformation. All right, so the molecule must have an anti-periplanar conformation where the beta hydrogen and the leaving group are coplanar in the same plane. So let's take a look at our example. We have a hydrogen, beta hydrogen, and our leaving group in the same plane. If they're all lines, solid lines, then they're in the same plane. Wedges and dashes are in and out of the plane. But the elimination must occur when the beta hydrogen and the leaving group are not only in the same plane, but are also in the anti-position. So anytime they're in the same plane, that means they're coplanar. But there's two coplanar configurations we'll talk about. We have to have an elimination that proceeds through an anti-periplanar, just means coplanar configuration. So let's take a look at these two different coplanar configurations, keeping in mind the anti is the one that will allow the E2 reaction to occur. All right, so our two coplanar geometries, we have where we're focused on our beta hydrogen and our leaving group. Anti is when they're on opposite sides. Syn periplanar is when they're on the same side. So opposite sides or anti, and same side means syn periplanar. So anti-periplanar or anti-coplanar gives us the staggered anti-configuration. It's lower in energy. The syn coplanar, this is an eclipsed conformation, and we know that this is higher energy. So we're going to say right now that E2 reactions will only go through an anti-periplanar geometry. All you have to know is that the beta proton and the leaving group have to be in the same plane but on opposite sides. They need to be anti to one another. All right, so when we eliminate the beta proton and the hydrogen, right, if we're looking at this from a Newman projection perspective, right, these are going away. Your base takes those, so what do we get? The elimination product. So we're not seeing the double bond in between, but we can just sort of flip this. In this case, we're flipping this up to get the alkene product. It doesn't matter which way you flip it. They're just flipping it here to show you the double bond because you can't see the double bond in the Newman projection. So if we're going to predict the products of the E2 reaction, keeping in mind that we must proceed through an anti-periplanar, we're first going to look for our beta proton and our leaving group. So the alpha carbon is the one that has the leaving group. And then the beta carbon has the beta proton. So let's ask ourselves, are the beta proton and leaving group, are they in the same plane? Yes. Are they anti to one another? Yes. So when the base comes along and removes the beta proton, and then we kick out our leaving group, what are we left with? Let's kind of draw it like it is on the left, and R1. It doesn't matter what these are. We're just designating them R1 and R2 to be different. So we can draw our alkene like this. On the bottom molecule are beta proton and leaving group are coplanar and they're anti. So this is the correct conformation for the elimination to occur. When the elimination occurs, let's just keep our wedges here. That was R1, wedge R2, dash R1, and dash R2. We draw our alkene, R1, R2, R2, and R1. Let's look at an example of stereospecificity. We know we're dealing with stereospecificity when we have a single beta hydrogen that can be removed. I have two beta positions, but the other one has three methyls. So we're not dealing with an issue there. There's no hydrogens that can be removed. The E2 reaction must proceed through an anti-periplanar. We see that the hydrogen and the leaving group are not anti to one another. If one was a dash and one was a wedge, that would be all right. Or if they were solid lines, they would have to be opposite of each other. But if you're unsure, just draw a Newman projection, because you can always rotate the Newman projection to the correct conformation to carry out the problem. And that's what we're going to do. Let's simplify our structure. I've got my chlorine. There is a hydrogen here. This group we'll call tert-butyl. I've got my hydrogen. I've got a methyl. We'll call this an ethyl group. So let's look at our molecule from this perspective and draw our Newman projection. I have my Y at the top. There we go. In the front, on the left, I have my hydrogen. I have my methyl and the ethyl at the bottom. In the back, I have my tert-butyl, my chlorine, and I have my hydrogen. Now, for this elimination to occur, the hydrogen, the beta hydrogen, and the leaving group have to be anti-periplanar. They are not, so we're going to have to rotate one of our carbons so that these are, or we're going to have to rotate this single bond, okay, in order to get the anti-configuration. So I'm going to hold the back the same and rotate the front carbon. Doesn't matter which one you do, but I'm going to rotate the front. Keeping the back locked in place. So my tert-butyl, my chlorine, my hydrogen. I'm rotating that hydrogen over there. My methyl comes down, and here's my ethyl. All right, now I have my leaving group and my beta hydrogen in an anti-periplanar configuration. The elimination can proceed here. So basically, when my base comes along, you don't necessarily need to draw this mechanism. You can't really show the arrow, that second arrow, but either way, the beta hydrogen and the chlorine are being removed. So what's happening here is essentially we're going to take this. I'm going to come up here and just redraw it to simplify this. I'm going to draw everything without the beta hydrogen. Oh, that was a tert-butyl. Okay, so I've removed the beta hydrogen and the chlorine. This is what I'm left with. Now we can just flip this to the right or to the left to draw the alkene. I'm just going to flip it to the right. Tert-butyl, hydrogen, ethyl, and methyl. That would be the strategy for solving this problem. All right, let's take a look and identify the major and minor products for the following E2 reaction that occurs when the substrate is treated with a strong base. Well, because I've got two beta hydrogens on the same carbon, I know I'm dealing with an issue of stereoselectivity. That means cis or trans. All right, so we can draw a Newman projection and then draw both products here. Let's call this hydrogen 1 and hydrogen 2. It's the same Newman projection I had before. I'm going to look at it from this perspective. H2, H1, ethyl, tert-butyl, my chlorine, and I had a hydrogen here. So here are my beta protons. One of them is already, hydrogen 1 is already anti-periplanar with the chlorine. So let's draw our first product. If we get rid of the hydrogen in the leaving group, all right, I end up with a Newman projection like this. I can just flip it over to the right. H2, tert-butyl, H, and my ethyl group. So that's if I remove H1. But what if I want to remove H2? I'm going to have to rotate this. Let's draw a new Newman projection. I'm going to keep the back the same. All right, now H2 is anti-periplanar with my leaving group. All I did was rotate the front carbon here. Okay, so if I remove H2 in my leaving group, I get something that looks like this. All right, do you see the difference in the products here? I have my hydrogens on opposite sides. This is your trans product. And my hydrogens are on the same side. This is your cis product. This occurred because I had two beta hydrogens on the same carbon, which gives rise to stereoselectivity. And you could probably guess what the major product here is going to be. It's the trans. And our minor product is the cis. All right, in this problem, we're going to do the same. We're going to predict the products of the E2 reaction. We're going to consider regiochemistry here and stereochemistry. All right, so I know that the carbon with the halide is my alpha carbon, and I have beta carbons that have two different sets of hydrogens. Right there, this tells me that I'm dealing with regiochemistry. Regioselectivity, remember, arises when we have beta hydrogens on different carbons. So now I have to look at my base. This is a non-bulky base. which means my Zaitsev product is going to be the major product. All right, so let's start with the carbon on the left, or the hydrogens on the left. So we've got a methyl with 1, 2, 3 hydrogens. When the base removes these hydrogens, I'm going to end up with the following alkene. All right, but what if I want to remove the beta hydrogen that's on the right? Well, this hydrogen needs to be anti-periplanar with the leaving group. It's not looking like they are, so let's draw a Newman projection and then rotate it if we need to. Okay, let's simplify our molecule. Here's my beta hydrogen, my methyl. This was an ethyl. There's my bromine. There was another hydrogen, and this was a methyl group. All right, so let's look at this from, we can look at it from this perspective now. And let's draw a Newman projection. Bromine, hydrogen, methyl, ethyl, hydrogen, methyl. Now my leaving group and beta hydrogen need to be anti-periplanar. So what I can do here is simply to just rotate the front carbon to the left. Keep the back locked in place. Now I've got my beta hydrogen in my leaving group, anti-periplanar in the anti-staggered configuration. So when the base comes along and removes the beta proton, my leaving group is going to disappear with its pair of electrons, and I'm going to get rid of that beta proton. And I'm going to end up with the following. I'll work down here. All right, so let's flip this on its side. Let's flip it over to the left. I have a methyl, the hydrogen, which I don't need to draw. I have my ethyl and my methyl. So I've got my two products that I've just drawn. I have a di-substituted, and I now have a tri-substituted. So this product here, the tri-substituted, this is my Zaitsev product, which will be the major product. My di-substituted is going to be the Hofmann product, which will be my minor product. All right, let's look at how to deal with a substituted cyclohexane that could undergo an E2 elimination. It's very straightforward. There's two rules you have to follow here. The beta hydrogen and the leaving group must be anti-periplanar like all E2 reactions. And your leaving group has to be in the axial position. So two rules. One, anti-periplanar. 2, leaving group has to be axial. Okay, so let's look at the example. If you have your leaving group axial, if you were to draw a Newman projection, you'd see that it would be anti-periplanar with the beta hydrogen. But if you draw your leaving group equatorial, as it is here, there are no anti-periplanar hydrogens that can be removed. That's a CH2 group here, not a hydrogen that can be removed. All right, so you must have your substituent that's going to leave your leaving group in the axial position. So let's look at some examples here. Instead of going through the transition states and drawing the chair conformation, I'm going to show you the trick for doing these. All right, so remember, 2 rules. The anti-periplanar rule, and we have the rule that the leaving group must be axial. All right, so anti-periplanar just means that your leaving group and your beta proton have to be opposite. And I'm going to show you a trick. Here's your leaving group. Let's identify all the beta hydrogens. Alpha, beta, beta. I've got a beta proton here. And then I've got one here and here. The trick is that your leaving group, if it's a wedge, or if your leaving group is a dash, the beta hydrogen must be a wedge. So look, our leaving group is a dash. This hydrogen here is a wedge, so this one is not going to participate in the E2 reaction. However, I do have an adjacent hydrogen that's a dash, so to eliminate the need for drawing the chair conformation, making this really overcomplicated, what we can do is just eliminate our leaving group that was a dash and the beta hydrogen that was a dash, or was a wedge. We keep our methyl group here, and the double bond goes in between the beta hydrogen and your leaving group. Let's look at the next one. Now, I've got a non-bulky base, so if regiochemistry arose here, we'd be looking for the Zaitsev product. However, let's just see what we're dealing with in terms of our hydrogens. My leaving group is a dash. I've got my beta hydrogen that is also a dash. I've got one here, and I've got one here. The leaving group has to be opposite or anti-periplanar to the beta hydrogen. So this beta hydrogen, they're both dashes. That doesn't work. However, this beta hydrogen is a dash, or sorry, is a wedge. My leaving group is a dash. So this will end up giving me a anti-periplanar configuration in one of the chairs, which we don't have to draw out. And I get my double bond right here. All right, let's take a look. With our next problem, I've got my leaving group is a wedge. I've got a hydrogen that's a dash. I've got a hydrogen that's a wedge. 2 hydrogens that are wedges and dashes. So I can eliminate my leaving group and this hydrogen, or I can eliminate this hydrogen. Let's draw both products and then we'll figure out which one is the major and minor product. Let's remove this one first. Okay, and the second one, if I remove the other beta hydrogen here, I get my double bond right there. Tert butyl group stays. Okay, so I've got a di-substituted versus a tri-substituted. I'm dealing with a non-bulky base. All right. So technically, this is your Zaitsev product, and this would be your Hofmann product. And we would predict that this could be our major product, and the di-substituted would be our minor. However, there probably are some steric considerations here that would affect the rate of these reactions. That tert butyl group is pretty bulky, so that might affect this, but let's leave that out right now while we're just learning the basics. So if we're in a situation where we have two beta hydrogens on different carbons, we can identify the major and minor by looking at the base. These alkoxides, these small alkoxides, are non-bulky, so they will afford the Zaitsev product as your major product.